spending 29 minutes in the computer lab working on column questions. You need to finish as many of the column questions during the class period as you possibly can. The working period may be open for a few hours after that, but for the most part, you need to finish them during class. Let's look at a few questions that are actually from the assignment just to clarify some things and give you some additional help. So this question, and you will be working on topic 11, those are the top ones you need to finish. And here I'm looking at question 1, and it says one of these statements is true. So this is just like a multiple choice question. You're looking for the correct answer. Let's see. And in this problem we see the word vapor and vapor pressure several times. I need to be sure we clarify that, but let's start here at number 4. Changing the water vapor into liquid water is an endothermic process. So if we have vapor and we're going to change it to a liquid, we're going to have to make energy leave this system. So that's actually exothermic. So that is not the correct answer. Let's look at number 3. Sodium, potassium, and calcium do not react with water. Yeah, right. You know that's not true. Here's this term vapor pressure of a liquid. At its boiling point is equal to half the prevailing atmospheric pressure. Now, it actually, at the boiling point, these things are equal. The boiling point at the vapor pressure at the boiling point is equal to the prevailing atmospheric pressure. That's the definition of the process of boiling, and we'll get to that a little bit later in this unit, hopefully. But what is vapor pressure? Well, if you have a container, like maybe a gas can, and it has a lid on it, the gasoline evaporates and you get a certain amount of vapor pressure in here, and you've experienced this pressure. You take off the lid, that pressure is released. So that's what it means by vapor pressure. And so the lower the intermolecular attraction between these particles, the greater the vapor pressure will be at any given temperature. Let's look at A and see if it is correct. If it's not, the answer will be none of the above. Liquid A boils at a lower temperature than liquid B. Okay, so this indicates that liquid A has a higher vapor pressure than liquid B at a particular temperature. So if it has a higher vapor pressure, that means that the particles are going to fly apart more easily, so it's going to boil at a lower temperature. Let's see. Boils at a lower temperature, higher vapor pressure. That is correct. Higher vapor pressure, lower boiling point. There we go. A is the one, number 1 is the one you would click. So, of course, your question may look a little bit different than that, but hopefully that clarified a few things. Which of the following has the highest boiling point? Well, we see here that this is nonpolar, so that's going to have a very low boiling point. You know that this is nonpolar. You know that dry ice has a very low boiling point. And so when it comes to looking at these other things, this is pretty polar. So that is going to have a low boiling point compared to these. This is pretty non-polar and fairly small. This isn't too polar, but it's really pretty big. So it probably comes down to something between these two, and it's going to come down to probably the thing that's the largest. So the largest molecule in this case may have the highest boiling point. Of course, it's also the thing with the largest dipole moment. And so you kind of have to give some thought to which is going to have the largest dipole moment here. And it turns out to be number 1. Which of the following statements is false? So that means everything else is true. And let's just check this. In a solid substance, the intermolecular force outweighs kinetic energy of the molecules. And that's true. If the intermolecular force that's attracting them is greater than the kinetic energy, it's going to be a solid. A substance with a higher boiling point has a weaker intermolecular force. No, weaker intermolecular forces make low boiling points. So that's the false one you're going to answer. Let's look at number 3. In a liquid substance, the intermolecular forces are approximately equally balanced against the kinetic energy of the molecules. I kind of like that definition. Number 4, the kinetic energy of a substance in a gas phase is higher than the kinetic energy in a liquid phase. Of course, to be in a gas, it's going to be a higher temperature. Temperature equals average kinetic energy. So number 4 is definitely true. So number 2 looks like a pretty good answer. Polar, 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 polar. Yep. It looks like number 4 is the only thing that is nonpolar. In other words, it does not have dipole-dipole interactions. Looks like we're skipping here to number 3. This is part 3. And let's see if we can make that a little bit bigger here. In general, the weaker the intermolecular force of a substance. So, weak intermolecular force, weak intermolecular force. What does it do? Well, it means the particles do not need as much kinetic energy to come apart, and so it's going to have a lower boiling point. It's going to have no dipole moment. I don't know, I'm thinking about this, trying to see what's wrong with that statement. Other than you can certainly have weak intermolecular forces that have no dipole moment. That's the only reason I can cross that one off. And the more it deviates from the ideal gas behavior. Now this is just the opposite. The stronger the intermolecular force, the more it deviates from the ideal gas behavior. And we had that van der Waals equation to help us account for that. So not good and not real good. So the best answer is definitely number 4. Now this is a multiple part problem. As we move to part 3, we're looking at nitrogen, phosphorus, astatine, and antimony are all in the same family of compounds. And so here they're all combined with hydrogen. And their boiling points are listed here. And we see that one of those is significantly higher than the others. And I'm looking at this and thinking, they must have some problem here with this. What they have some problems with is this number right here. Let's see, let me think about graphing this. Ammonia would be 33, this would be much higher. And because we should see the hydrogen bonding in the ammonia, which would make it have a much higher boiling point. And I really think that whoever made this problem accidentally switched these two numbers. So when you come to this, ammonia has an elevated boiling point because the hydrogen bonding should be the correct answer, but I'm not seeing that in their data. Let's look at the next slide and see if they've fixed that. No, they haven't in part 3. So when you come to this, it says except for ammonia, the boiling point increases as we move down the group in the periodic table. Which explanation of this trend is correct? And it is that the boiling point increases when we get to heavier elements because we have a stronger dispersion interaction. That's the thing that I referred to as sloshability, but I said more correct term would be polarizability, and they're saying a stronger dispersion interaction is the correct answer. And those terms, I agree with their answer, but once again, they have something out of order here. So don't forget that when you're coming to question 7. It's a 3-part question, and that the third part is about the boiling point increases because of heavier elements have a stronger dispersion interaction. Got that? Yeah. Okay, let's move to the next question. Liquids A and B are in identical beakers under the same conditions of temperature and pressure. Liquid A evaporates more rapidly than liquid B. Well, what that really means is if you have liquid A and liquid B in these containers, and what they're not saying is I think we should have a lid on these. Based on this information, one can conclude that liquid A has, I'm reading them again here, liquid A evaporates more quickly than B, so that means we get a lot more vapor up here in liquid A than we do in liquid B. So this has a higher vapor pressure. That's what vapor pressure is all about. And what are the primary intermolecular forces present in solid carbon dioxide? Oh, you should be able to get this. We call them by several terms. Van der Waals, or temporary dipole. But here they're calling them London dispersion forces. Don't forget that term. Now notice we've skipped a few questions, so there were some others in here that you should be able to get, and good luck with that on Wednesday.